Okay, think about this for a second. If I ask you to mentally map the route from your front door to, say, your favorite coffee shop, you could do it, right? Including that awkward three-point turn you always have to make to avoid that one fire hydrant. We perform these incredible spatial tasks completely effortlessly. Navigating a new parking garage, finding your car just by the sound of an AC unit, and then instantly generating a plan to get back out. That seamless, deep sense of space. It's just fundamental to how we think.
It's not just fundamental, it's the cognitive architecture that lets us exist in the world. And for years, when we've been testing these uh, multimodal large language models, the
The ones
MLLMs,
that can see and read.
exactly, we've relied on these really fragmented task-specific tests. Did the robot crash? Did it see the stop sign?
Hmm.
But those tests don't tell us how the model is actually thinking in 3D space.
Right. And that's what this deep dive is all about. We're looking at some groundbreaking research that introduces something called the SpatialBench framework. And this is really the first systematic, cognitively grounded way to evaluate these models, moving away from just did it pass or fail.
The mission here is to move from simple task completion to a real ability-oriented analysis of spatial intelligence. We want to answer one critical question for you. How close are these incredibly powerful AIs to truly grasping the geometry, the rules, and the causality of our world?
And we're going to give you the spoiler right at the top because it's the most important finding. MLLMs, they have incredible eyes. They're amazing at low-level visual perception.
Hmm.
But their intelligence just drops off a cliff. I mean, a sheer dramatic cliff the moment the task demands higher-level reasoning or planning. So today we're going to unpack the 5 cognitive levels used in this research and show you exactly where the modern AI brain stalls out compared to ours.
To really get where MLLMs fail, we first have to understand what spatial cognition even is. The researchers built this framework by looking straight at neuroscience, specifically that cognitive map theory.
Oh, this is the theory that won a Nobel Prize, isn't it? The idea that mammals, including us, we build these, like, internal maps inside our brains.
Precisely. These internal maps encode everything from metric distances to topological relationships. The key insight for AI evaluation is that spatial knowledge isn't one single skill. It's a progressive, hierarchical process. You start with raw sensory data, and you build step by step toward this abstract, usable mental model. SpatialBench basically treats AI intelligence the same way.
And that structure is what makes the whole analysis so powerful. The research sets out 5 progressive levels. So let's use that annoying multi-level parking lot, the one you're totally lost in, as our running example to make this feel real.
Okay, so we start at the foundation. Level 1, observation. This is the simplest step, purely about visual perception. For the MLM, this is just identifying objects and their basic attributes.
So in our parking garage, that's just seeing a red sedan, counting 5 columns to your right, or estimating that the payment kiosk is, I don't know, about 20 meters away. It's pure sensory input.
Then we move up to level 2, topology and relation. This is the first step toward understanding structure. The model isn't just seeing isolated items anymore. It's starting to encode the spatial relationships between them.
Okay, so we've spotted the red sedan, that's L1. Now at L2, the model asks, is that sedan next to my car? Is the exit sign to the left or the right of the ramp? It's all about relative position.
Exactly. Now, this is where the human brain makes a seamless jump and where the MLLM starts to sweat a little. Level 3, symbolic reasoning.
Okay.
This is the shift from just geometry to actual rules. The model now has to associate a visual symbol, just a squiggle of paint on the ground, or a metal sign with an abstract rule-based meaning.
Wait a minute. If an MLLM can read a text sign that says SDOP, and it can identify the red octagon shape, and it knows the sign is in front of the car, why is level 3 so much harder? Isn't that just basic stuff for these models?
That is the key question, isn't it? Because reading the word SDOP, that's linguistic. Recognizing the shape is purely visual. But understanding that the red octagon compels the car to stop, that it overrides everything else, that requires symbolic interpretation.
Yeah.
In the parking lot, it means seeing a dashed yellow line and knowing that implies two-way traffic.
I see. So it's the difference between describing a chess piece?
And actually knowing how it's allowed to move.
Precisely.
And that sets the stage for level 4. Causality. We're now moving into prediction. Physics, basically.
This is anticipating what happens next. The example from the research is perfect. If the Tesla suddenly accelerates backward, which event is most likely to happen? The model has to simulate the collision.
Yes, it has to infer where momentum will carry that car and what it might hit. It requires tracking velocity and trajectory, things our brains do intuitively. And that brings us to the summit, level 5, planning, the ultimate goal.
So this is integrating everything we've talked about. The observation, the relationships, the rules, the predicted outcomes, all to create a coherent plan. The final task in our parking lot. How do I get my car out of here from parking spot P4?
And that plan has to navigate obstacles, respect the traffic rules, avoid collisions, and sequence all of it into a useful path.
Okay, so armed with this 5-level framework, the researchers built SpatialBench. Tell us about the sheer scale of this thing.
It's massive. They used a multimodal data set with over 1,300 question-answer pairs. And crucially, these are from 50 egocentric videos, first-person perspective, exactly what an autonomous car would see. And the settings are really diverse. Underground garages, busy city roads, even forest trails.
So they put all the biggest and best MLLMs, your Geminis, your GPTs, your Quens, through this comprehensive ringer. And that is where the performance stratification becomes, well, brutally clear.
It was a shocking drop-off. I mean, if you look at the scores, the models were great on L1 observation and L2 topology and relation. They're exceptional perception engines.
They can see.
They can see, they can count, they can locate things. But the second the task moved into L3, symbolic reasoning, L4 causality, and L5 planning, the accuracy just plummeted.
What's the deep implication of that specific pattern?
It means that these MLLMs are fantastic at extracting visual evidence, but they struggle enormously to convert that raw evidence into abstract, actionable knowledge. The visual part of their brain seems almost decoupled from the high-level reasoning part.
So let's talk about the winners. Which model, even with this drop-off, showed the most promise?
Gemini 2.5 Pro was the clear leader. It had an average score of about 71.86. It consistently did better than the others, especially in those tough L3 to L5 tasks. It just shows that the scale and architecture of these big proprietary systems give them a real edge right now.
Any surprises from the open source models?
Yeah, mainly that scale is important, but it's not everything. Performance varied a lot, even within the same model family, like different versions of Qwen. This tells us you can't just throw more parameters at the problem. It's about how you design the architecture to integrate the visual data with the reasoning core.
Okay, so 71% for the best AI model sounds pretty good, I guess, until you bring in the human results. And this is the part of the research that should really make everyone pause.
Absolutely. The researchers gave the exact same test to 33 people. No special instructions. Humans achieved a near-perfect overall score of 96.4.
Wow, 96.4. That's practically zero error across this whole spectrum. But I have to ask, is that high human score just because the tasks were designed to target MLLM weaknesses?
It's a fair question, but here's the striking detail. It's where the human score was highest. On the hardest tasks, symbolic reasoning, causality, and planning human performance was essentially flawless, almost 100%. So these tasks reveal what robust intelligence looks like. The average person solves the hardest spatial problems instantly, while the best AI is still struggling.
So we have an MLLM that can describe a scene exhaustively but can't make a solid plan versus a human who does both perfectly. What does that look like in their thinking process?
The case study with the white Volvo S60 is the perfect example. The Volvo is making a right turn, and the question is, which destination will it pass next?
Okay, so lay out the human approach first. What's our brain doing?
The human approach is selective, goal-directed. We instantly see the Volvo's intent. It's turning right. So we immediately discard the other options because they're in the wrong direction. We focus only on the turning path and quickly identify the correct object. Our reasoning is efficient and focused.
And the MLLM?
Even the best one, Gemini, just gave this unfocused, descriptive narrative. It would mention all the different cars, the parking barriers, and it got confused tracking the movement of the camera instead of the Volvo. It lacked coherent spatial intent. It drowned in surface details instead of abstracting the one simple relationship needed to get the answer.
That distinction, diffuse attention versus selective abstraction, is everything. And it leads right into the systematic failures these models have. One of the biggest is something the researchers called egocentric reasoning breakdown.
This is where they just completely melt down. They can't manage different frames of reference. They mix up three distinct coordinate systems. The scene-centric, which is the fixed layout of the room.
The map.
The map, exactly. Then there's the camera-centric, what the recorder is seeing. And finally, the agent-centric, what the robot or car itself is facing.
Why is that so hard for them? I mean, a human toddler knows the difference between my left hand and the table's left side.
That's the billion-dollar question. Our brains are constantly doing this coordinate transformation. We have an internal sense of self, and we map the world to it. MLLMs, they seem to lack this continuous internal state, so they just default to the easiest frame, the camera's view. And when the camera turns, they lose track of what left or forward even means to them.
Give us a concrete example.
Okay, there's this indoor scene. A robot is on a projector facing a whiteboard. The question asks for the direction of an AC control panel relative to the robot. The correct answer, from the robot's point of view, is backward.
And the model has seen all the objects, so L1 is fine, but it fails the transformation.
It fails completely. It often predicts left. It has located the panel relative to the room and the camera, but when it tries that final, crucial step of mapping it to the robot's own perspective, it gets confused. It lacks a stable internal compass.
And that kind of flaw is just catastrophic when you go from locating an object to actually trying to navigate.
It is. Think about the route planning task. The robot is next to a motorcycle and needs to drive onto the main road. The correct first step is turn right. The MLLM says turn left.
Why the reversal?
Because as the robot moves to align with the road, the MLLM gets tripped up by the momentary camera viewpoint. It doesn't maintain the robot's own consistent heading. It makes a judgment that completely reverses the turn, proving this is a crippling failure for any kind of real-world navigation.
Okay, before we wrap up, let's quickly touch on in-context learning. What happened when they gave the models a hint, like a human-written explanation before the question? Did that help?
It was a fascinating split result. For the weaker MLLMs, like some versions of GPT and Quinn, giving them that one-shot guidance led to a substantial performance boost. It suggests their powerful language brain can be used to compensate for their weak spatial logic.
So if you tell them how to think, they can do better.
Precisely. But here's the kicker. The strongest model, Gemini 2.5 Pro, actually got worse on some of the intermediate levels when it was given the human prompt. Yeah. It implies that its own internal native spatial logic was actually more robust than the reasoning structure we tried to force on it. It works better when it's left to its own devices, imperfect as they are.
That is a powerful statement about how it was trained. So let's bring this all together. SpatialBench has drawn a very clear line in the sand for us.
The conclusion is unambiguous. MLLMs are master observers, that's L1 and L2, but they are not yet true spatial thinkers. They fundamentally lack that integrated cognitive map that's needed for genuine spatial intelligence at levels 3, 4, and 5.
So this research really gives AI developers a roadmap. It shows them exactly where to focus on multi-step reasoning, on integrating abstract rules, and fixing this inability to maintain a stable, agent-centric view of the world.
Without those targeted improvements, achieving robust general intelligence, especially in dynamic, real-world settings, it's still a distant goal.
We want to leave you with one final thought to mull over. If today's most advanced MLLM can struggle to remember where an object is or which way it's facing after a simple camera turn, what does that truly imply about the complexity and the reliability required for something like fully autonomous driving on a crowded highway, where the difference between a 71% accurate plan and a 100% accurate plan is the difference between life and catastrophic failure? That gap, that's the great challenge facing AI today.